Hello and welcome to this session. In this session we will see linear regression model. Basically we'll see the math behind it. Basically behind the math we understand, first we need to understand what's the assumptions of the model and what is OLS approach. So we have understood what is linear regression in the previous session. Please scroll through that video before doing the math behind linear regression model. So basically in linear regression we are going to find the best fit line among the scattered data points. So let's say these are the scattered data points. This is one, this is one, this is one. So basically the goal of linear regression is to find the best line. Right, because you can also have a line here, you can also have a line here. So basically how do you find out the best fit line? So to find out the best fit line, the goal is you plot a vertical line from the scattered data point to the line that you have achieved, you're trying to plot, and that line would be nothing but the error. So here they are also called as residuals. So these error line is nothing but E1, E2, E3. Find the sum of the squares, that is E1 square plus E2 square plus E3 square. So the line which gives us the most minimum sum of squares errors, that would be the best fit line. So this line that we have achieved would be mathematically given as y is equal to a0 plus a1x plus e, where a0, a1 are the coefficients of regression, a0 is the intercept which represents the bias, a1 is represents the slope of the line, and e is the error in prediction. So before we understand, go behind the math, there are 4 assumptions for this model. The first assumption is the output y is random, they are mutually independent of each other. So I will have y1, y2, y3, all are independent of each other. The second one is the error. So you are predicting the error, right, between the true value and the predicted value and the actual value. So the difference between predicted and true value is called as the error, and these errors are also independent of each other. I will have E1, E2, E3, they're all independent of each other. And the error is also independent of the value of x. Right, error term is independent of the value of x. X is nothing but your explanatory variable. The fourth one is you will have some unknown parameters in your regression model, which we call it as constants. So coming to the next one, before we go into the math, there's one important approach called as OLS approach, that is ordinary least squares approach. So basically this is the idea behind your linear regression model. Right, as we saw in the previous slide, right, we have a set of scattered data points, right, there's one scattered data point here, here and here. So we are the data points are now modeled using a straight line, right, and this vertical line is nothing but your E1, E2, E3, which we call it as residuals. So when we add it up together, E1 plus E2 plus E3, we call it as sum of residuals, and to get the line of best fit, right, we have to find the squares of these individual errors. The squares of the individual errors are E1 square plus E2 square plus E3 square. So basically when you get the minimum, wherever you get the minimum E1 square plus E2 square plus E3 square, that line would be called as the line of best fit. So basically OLS, that is ordinary least squares method, as the word itself squares, least squares, right, least squares of E1 square plus E2 square plus E3 square. So that is the goal of OLS approach. So it's an optimization method. OLS is an optimization technique where the difference between the data points and this line is optimized. So now let's go behind the math behind the linear regression model. So let's say this is our x-axis, this is our y-axis, and these are the scattered data points x1, x2, x3 and xn, and these are the dotted lines. These dotted lines are nothing but the errors or the residuals. So I have E1, E2, E3 and En. So as I've already said in the previous equation, mathematically you can using linear regression model, this is the line equation, right, y is equal to a0 plus a1 x plus e. Now suppose I have x values are x1, x2, xn, then y values are y1, y2, yn, and just write y1 is a0 plus a1 x1 plus e1, y2 is a0 plus a1 x2 plus e2, and so on. So basically for different values of x you get different values of y. a0, a1 they remain same because they are the coefficients, and e1, e2 up to en are the residuals. So if I want to find the error, right, then error, because that is my goal, I have to find the errors and I have to have the most minimum error. So to find the errors, what you have to do is just transpose this to the other side, and if I generalize it, then I get ei is equal to yi minus a0 plus a1 xi, where I ranges from 1 to n. So e is nothing but your errors associated with the data points, and they're also called as residuals. Now what is the regression line? As I said, regression line is the line of best fit where the sum of the squares of the residuals are minimum, right? So that means sum of the squares of the residuals is E1 square plus E2 square up to En square is minimum. So how do you write it mathematically is I already got this equation here, right? In the equation 3, just write it again here. But now I'll just take the sum, right? So just take the summation. E is equal to summation of ei. Capital E is summation of small ei, where I ranges from 1 to n. Summation of I is equal to 1 to n, yi minus a0 plus a1 xi. I have to take the sum of the absolute values. Absolute value means just the same equation, put the mod value. Okay. Now I have to minimize the sum of the squares errors, right? I have to minimize the sum of the square errors. So that means to this I just add a square. That's what I've done. To this I just added a square. So E is equal to summation of I is equal to 1 to n. Ei square is equal to summation of I is equal to 1 to n yi minus a0 plus a1 xi whole square. What you have to remember is, why do we take squares? We take squares so that we remove the effect of these negative values, because E1, E2, E3, they can be positive, they can be negative, or it can be even 0. To reduce that effect of negativity, we take the squares. So once you take squares, even negative will become positive. And why other thing is, since we have taken square, even a small change in error can make a big impact, and we prefer that in linear regression. So basically the goal of linear regression model is what? To minimize the sum of the squares errors, right? So rewrite the same equation. I have written the same equation here, but the same thing has been written here. Summation of I is equal to 1 to n yi minus a0 plus a1 xi whole square. But that is represented as j. In linear regression model, the minimization function is nothing but j. So remember this, j of a1 comma a0, where a1, a0 are nothing but the parameters, the coefficients of your linear regression model. J is nothing but the minimization function. So goal is what? To minimize this, right? We want to minimize j. So how do you minimize j? If you want to minimize j, you have to differentiate it with and equate it to 0. That's what we have to do, right? So differentiate j and equate it to 0. You do not have the differentiation in your syllabus, so I'm not going to work on this. So basically after differentiating, you would be able to get the value of a0 and v1. So after differentiating, this is the value of a0 and a1 that you get. a1 is this and a0 is this. So what you have to remember is, to do the problems on linear regression, you need to remember this value of a1 and a0. One thing you have to remember is, when you are doing problems, first find out a1, because the value of a1 is required here in a0. First find a1 and then find a0. So that's it for the mathematical form of linear regression model. In the next session, we'll meet again to solve some problems with respect to this. Thank you so much, and please subscribe to the channel.